Right, welcome to the AP Calculus AB exam review. If you've arrived at this point in the year, you've managed to survive AP Calculus, and you've also managed to see such awesome applications as how we can calculate the temperature of a potato at any time t using differential equations, as opposed to doing something simple like, say, stick a thermometer in the potato. In addition, in stark contrast to AP Physics 1, AP Calculus works strictly in radian, so please make sure your calculator is in radian mode and not degree mode. So topics we'll look at in this course or video series is not broken down by unit, but rather by specific topics that we've covered throughout the year. So we'll look at limits and continuity, differentiation and differentiability, function analysis using derivatives, FTOC and anti-differentiation, diffeqs and slope fields, applications to calculus such as related rates, rates of change, real-world scenarios, so on and so forth, 1D motion, and then lastly, areas and volumes between curves. So let's move on to day one, limits and continuity. Limits and limit properties. All right, so a limit describes the value that a function f tends towards or arrives towards as x approaches a specific value a. Again, we talk about patterns and trends of what f approaches. We do not talk about what f actually is at that point because, as we've seen throughout the year, that the limit as x approaches a does not need to actually be equal to the actual function value at x equals a. So as a result, the limits are more about patterns and tendencies of the function as opposed to what the function actually is equal to at a point. It follows the trends of the curve of the function. For a limit to exist at a point, we have the condition that the limit as x approaches a from the left side must equal the limit as x approaches a from the right side. To evaluate limits of indeterminate forms, i.e. 0 divided by 0 or infinity divided by infinity, where substitution does not work, we can either resort to factoring for rational functions, conjugation for square root limits, or L'Hopital's rule if we approach an indeterminate form that does not fall into the two above categories. L'Hopital's rule only works for indeterminate forms like the limit as x approaches a, f of x divided by g of x. So in that case, when we get an indeterminate form, the equivalent limit is equal to limit as x approaches a of f of the derivative of x divided by the derivative of g. And yes, you can see a little bit of typo there, but still the idea remains the same. So as an example, we can see that as x approaches 1, the limit does not exist because as x approaches 1 from the left-hand side, our function value is negative. Our function value tends toward, better said, negative 1. While we approach 1 from the right side, we see our function value tends towards 0. However, f of 1 does exist because we can see that there's a closed dot right here, so f of 1 is equal to 2. F of 0 does not exist. F of 0 does not exist because we have an open dot right here and there's no closed dot anywhere where x equals 0. But what we can see is that as x approaches 0, we do have a limit because from the left-hand side and the right-hand side, our function tends towards the same specific y value of 2. Lastly, we get to the squeeze theorem, where if we're given two functions g and h with the property that both the limit of h and g as x approaches a is the same, let's call it L, and we have a function f that's between g and h around x equals a, then f is going to be squeezed and forced by h and g to have the same limit as h and g as x approaches a. Put more succinctly, if f is between g and h around x equals a, and g and h both have the same limit at x equals a, then the limit of x, or limit of f as x approaches a, is equal to the limit of g and h as x approaches a. Again, please note that these two conditions, that f must be between g and h around x equals a, and that the limit of g and h as x approaches a must be equal. Both these conditions must be met in order to apply the squeeze theorem to an unknown function f. End behavior. Again, end behavior, when they ask you for a horizontal asymptote, that's asking you for the limit of a function as x approaches positive infinity for one asymptote and negative infinity for the other asymptote. There are some cases where the horizontal asymptote will be the same as x goes to both plus and minus infinity, but in general that's not true, so you have to evaluate each one separately. Some useful limits to know. The limit as x approaches plus or minus infinity of the reciprocal function is always equal to 0, and then the limit as x approaches positive infinity of e to the negative x is equal to 0, or better said, a to negative x for any base is equal to 0. This describes exponential decay. Limits involving these two can be treated by substitution. Hence, if we have a function a to the 4 minus 1 over x, and we take the limits x approaches positive infinity, we can replace 1 over x with 0, and that gives us a to the 4th as our horizontal asymptote. To determine the end behavior of rational / quasi-rational functions, you're going to focus on leading terms of top and bottom and evaluate the limit of resulting power. If you have a horizontal asymptote for x going negative infinity, remember to swap out the x's in your function for negative x, so that way your limit goes to positive infinity, and then all your terms contain negative x to a certain power. That is very important for square roots, especially if the non-square root power is odd, because that will change your horizontal asymptote depending on whether x goes to positive infinity or negative infinity. The alternative is that you can use L'Hopital's rule to evaluate end behavior. Again, this only applies to indeterminate forms. Continuity. In order for a function f to be continuous at a point x equals a, f of a must exist, limit as x approaches a of f of x must exist, and the limit must be equal to the function's actual value at x equals a. If any one of these conditions fail, the function is not continuous at the point, and thus our function, is not continuous. All three conditions have to be met. It's kind of like a failsafe. Anyone's not met, then the function is not continuous. As an example, say that we have f of x equals 5 minus 2x for x less than negative 3, and f of x equal to x squared plus 2 for x greater than or equal to negative 3. The first thing we have to check is whether or not the function value actually exists, which means we're just going to plug and chug negative 3 into our function value. At x equals negative 3, we see that our function value is x squared plus 2, so our function value is negative 3 squared plus 2 equals 11. Next, we have to check the left-hand and right-hand limits, okay? For x less than negative 3, okay, our limit is going to be based around 5 minus 2x, because that's our function value at that point. That's our function for x less than negative 3, and we get a resulting value of 11. For x greater than negative 3, our function value is going to be x squared plus 2, so our limit as x approaches negative 3 from the right is just going to be the same thing as f of negative 3, 11. Hence, we can see we get the same value for both left-handed and right-handed limits, so our limit does exist, and it's in fact equal to 11 as x approaches 3. Negative 3 should stay right here. Don't know what happened to negative 3. And lastly, by comparing, we can see that the limit as x approaches negative 3 is in fact equal to the function value negative 3. Hence, f is continuous at x equals negative 3. Classifying discontinuities based on which requirement fails, there are three types of discontinuities at point x equals a. Vertical asymptotes / infinite discontinuities. F of a does not exist, and the limit does not exist because the left or right limit, one or the other, doesn't have to be both, but it could be, is plus or minus infinity. A jump discontinuity occurs if f of a does exist, but our limit as x approaches a of f does not exist because the left and right limits are not equal to each other. You get two different y values, two different finite y values, better said, and thus there's a jump from one y value to another y value at x equals a. A removable discontinuity occurs if f of a does not exist, but the limit as x approaches a of f of x does exist, or f of a and the limit exist, but they are not equal. So again, here's an example. We can see that jump discontinuity. We jump from one y value to another. So our limit does not exist as x approaches a. A removable discontinuity, we can see right here that our function value does not exist, but we still approach a specific y value, okay? So our limit does exist. Or we could have a closed dot up here, which means our function value would exist, but it's not equal to the limit as x approaches a. And lastly, we can see from infinite discontinuity that our limit does not exist. From the left-hand side, we approach positive infinity, and from the left-hand side, we approach from the right-hand side, we approach negative infinity. And lastly, we look at the intermediate value theorem. Recall that if a function is continuous over a closed interval, x greater than or equal to a and less than or equal to b, then if n is a number such that n is is greater than or equal to the value of f of a, but less than or equal to the value of f of b, then there must exist a point x over c, x equals c over the closed interval such that f of c equals n. Again, we can think of this as a guitar string theorem or the no lifting pencil theorem. That's not as catchy. So again, the uses are determining if a solution is guaranteed to a certain equation over an interval, i.e. is it guaranteed over a certain interval that there is a c such that f of c equals blah blah blah, or the number of times at minimum or at least that f of x is equal to a specific value over said interval. And this concludes day 1 of the AP Calculus review.